present about Gibbs free energy. Let's see our video.
Hello everybody, back with us in this lovely occasion, and we would like to present the thermodynamic in Metalurgi Kel, and in this part we would like to discuss about Gibbs free energy. In this part there are 5 points that would be presented by us. Like the first, what is Gibbs free energy? And the second is formulation of standard Gibbs free energy, and the third is temperature and free energy, and the fourth, free energy and equilibrium constant, and the 5 is metallurgical thermodynamic. Well everybody, let us begin.
What is Gibbs free energy? Gibbs free energy is a thermodynamic property that was defined in 1876 by Josiah Willard Gibbs to predict whether a process will occur spontaneously at constant temperature and pressure. Gibbs free energy, G, is defined as G equals H minus T multiplied by S, where H, T, and S are the enthalpy, temperature, and entropy. The Gibbs free energy of the system is a state function because it is defined in terms of thermodynamic properties that are state function. The change in the Gibbs free energy of the system that occurs during a reaction is therefore equal to the change in the enthalpy of the system minus the change in the product of the temperature times the entropy of the system. Standard Gibbs free energy. This is its equation for standard energy at state condition. Therefore, our standard state condition, the partial pressure of any gases involved in the reaction is 0.1 megapascal. The concentration of all aqueous solution are 1 molar, and tabulated standard rate thermodynamic data are generally for a temperature of 25 degrees Celsius or 298 Kelvin. And how we get this equation? And this is equation we have multiplied by minus T, and we get minus T multiplied by delta S total equal delta H minus T delta S, and delta S total equal delta G.
Standard Gibbs free energy. The standard state free energy of formation is symbolized by delta G degree formation. When we have the chemical reaction like A plus B produce C plus D, we can calculate the delta G by sigma delta G of product minus sigma delta G of reactant. According to the chain of the energy of reaction, we can suppose that delta G degree more than 0 is non-spontaneous, and delta G less than 0 is spontaneous. The relation of Gibbs free energy with enthalpy and entropy is shown by these blocks. When we have the entropy more than 0 and enthalpy less than 0, we have the spontaneous reaction. And when the entropy is less than 0 and enthalpy more than 0, the chemical reaction is not spontaneous. And how about this one? The entropy is less than 0 and enthalpy more than 0. Could we imagine that? Yes. This is temperature dependent. When the temperature is high, this reaction is spontaneous, and when the temperature is low, the reaction is not spontaneous. And for this reaction is spontaneous when the temperature is low. Okay. Free energy and equilibrium constant. The following equation relate to standard state free energy of reaction with the free energy of reaction at any moment in the time during reaction. We have this equation. Delta G is equal to delta G standard plus epsilon K. And this is the equation where the reaction is equilibrium. Move this equation to the right and we get this equation. Delta G standard is equal to minus epsilon K. Metallurgical thermodynamics
that is used to heat it is a large steel structure lined with refractory fire bricks that can withstand temperatures approaching 2000 degrees Celsius. Although the origin of the blast furnace dates back to Han China in the 1st century BC, it was in 1709 that Abraham Darby developed a blast furnace that could be fired by coke instead of charcoal, which paved the way for modern-day blast furnace. Traditional blast furnaces are chimney-like structures which are actually 80 to 100 feet wide and 30 meters high, made of iron or steel and used chiefly in the process of smelting, that is deriving a metal out of an ore, in this case steel out of iron ore. The principle involved in this means of extracting metals is that of the reduction of the ores by the action of carbon monoxide, that is, the removal of oxygen from the metal oxide in order to obtain the metal. Lined with fire brick, the furnace is narrow at the top, increasing in diameter downward, but narrowing again suddenly almost at the bottom to form the hearth or crucible where the fine molten products are caught. The furnace is fed from the top, which has an entry referred to as the charging hole, with a charge of definite quantities of ore, coke and flux, consisting mostly of limestone that is carried over the charging ramp. Water is then released, which travels through one end of the water channel and pours down from the other end, hitting the water wheel, which acts like a turbine. The water wheel starts rotating due to the pressure and the flow of water, causing the mechanism of cams to also move, eventually striking the tuyeres to bellow instantaneously. Thus, preheated compressed air is introduced at the bottom through tuyeres, entering just above the crucible. The air passes upward through the charge, where coke is burned to form carbon dioxide and heat. The heat decomposes limestone into calcium oxide and additional carbon dioxide. Carbon dioxide oxidizes coke to form carbon monoxide at a high temperature of 1200 to 1300 degrees Celsius. The carbon monoxide then reduces the ore to iron, taking on oxygen and reverting to carbon dioxide. This gas, together with unused carbon monoxide, nitrogen and other constituents of the air originally introduced, is let off through a pipe from the top of the furnace and, being still at a high temperature, is employed to heat the stoves into which fresh air for the process is brought. As the operation proceeds, the mass in the furnace becomes molten and descends into the crucible. The iron sinks to the bottom. Impurities, called the slag, being lighter, float on the top. The slag is drained through a pipe in the upper portion of the crucible, which is called the slag pipe. The iron is tapped from below and is run into sand molds to harden. The product is known as pig iron or cast iron, and the place where it is hardened is referred to as pig iron bed.
Metallurgical thermodynamic. In this part, we will use the Gibbs free energy equation to calculate the Gibbs free energy in the blast furnace process. This is the blast furnace, and there are chemical reaction there, like Fe2O3 plus 3CO produce 2F8 and plus 3CO2, and this following reaction. To calculate the Gibbs free energy from this reaction based on Lewis paper, at first using Gibbs equation. This is the equation 1, and this is the equation 4, 2 and 3, and the last one, we have to know the entropy and enthalpy data standard state at any temperature. These are the data.
Hello everybody, I will to tell you about the example Gibbs energy in a blast furnace. Consider the direct decomposition of rust to iron like this. 2Fa2O3 solid state become 4Fa solid state plus 3O2 gas state. Delta G equal plus 1487 kilojoule. This large positive value for free energy tells us the reaction is non-spontaneous. However, this does not mean you cannot change the rust back to pure iron. You just need to do some useful work to reduce it by coupling with a reaction with a large negative free energy, like 2CO gas stage plus O2 gas become 2CO2 gas stage with a delta G equal minus 514 kilojoule. The common terms in both reaction is O2 gas. Notice we have 3 as product in rust decomposition and 1 O2 gas in the CO gas combustion, like this. Solid state become 4Fa in solid state plus 3O2 gas state, and delta G equal plus 1487 kilojoule. 3 times 2CO gas plus 2O2 gas become 2CO2 gas state, and delta G equal minus 540 kilojoule. Overall is 2Fe2O3 gas plus 6CO gas state become 4Fa as solid state plus 6CO2 gas states, and delta G equal minus 56 kilojoule. Thank you. Ada nggak?